All right, we're here today with Dr. Jacob A. George, the Sulzbacher Chen Endowed Professor in the John and Marcia Price College of Engineering's Department of Electrical and Computer Engineering and the Spencer Fox Eccles School of Medicine's Department of Physical Medicine and Rehabilitation at the University of Utah, which is quite a mouthful. But Jake, if you can just briefly introduce yourself and tell us a little bit about your tenure so far.
Yeah, so I'm faculty at the University of Utah, where I direct the Utah NeuroRobotics Lab. And my lab works on assistive, rehabilitative, and diagnostic technologies for individuals suffering from life altering neuromuscular impairments, things like stroke, traumatic brain injury, spinal cord injury, or limb loss. And we work with a variety of other different patient populations to try to develop more accessible technologies and interactions with different types of technologies in our real world. So some of the key things we are developing are more efficient ways for individuals to interface with the world around them,
Mm-hmm.
using more accessible tools that are available to them to help them, complete tasks that are fundamental to their activities of daily living. So, for example, helping an individual, um, you know, go and ski again on a mountain, for example, after having a spinal cord injury, or helping an individual learn to cook again using a prosthetic hand or an
Mm-hmm.
exoskeleton. These are kind of some of the core research elements that we do in my lab, and we focus a lot on the control side of how do we extract information from a user or provide information back to a user to give them a more dexterous way to interact with assistive technology.
You sort of touched on this, but I know as the director of the Utah NeuroRobotics Lab, your work kind of sits at the intersection of rehabilitation robotics, sensory, motor, neural engineering, and bio inspired artificial intelligence. Can you break that down into layperson's terms a little bit and explain how you zeroed in on that particular area of research?
Yeah, so there's three different areas that you described, and those are all different core pillars of things we do in our lab. But in simple terms, what we're trying to do is we're trying to take a person who's, for example, lost a limb or lost the ability to control their limb, and give them that functionality back. And
Hmm.
so let's take, for example, an individual who has a spinal cord injury or a stroke, and their hand might be paralyzed. In order for them to now interact with the world around them, they can't do it through our natural way of, moving our hands and grabbing, clicking remotes or pressing buttons. So what we often would do is, like, for example, connect a person with a piece of assistive technology or a rehabilitation robot. And so that's really the first key piece. That could be an exoskeleton device that helps move a person's hand who's paralyzed, or it could be a prosthetic limb for a person who's lost a limb, or it could even be some sort of, adaptive wheelchair or adaptive skiing system or something like that, that is a physical device that allows a person to have some sort of mobility and or sensation coming back from the environment. And so that's what we mean by rehabilitation robotics. It's like, what is that piece of technology that allows a person to interact with the world? And then now the question is, how do we actually allow a person to control that technology?
Hmm.
And, you might think, well, you can use voice commands, but voice commands have all sorts of different types of limitations. And so really what we do in our lab and what we specialize is trying to provide intuitive and dexterous control of these technologies. And the way we do that is through brain computer interfaces or neural interfaces. And this is this idea of allowing an individual to use their thoughts or their intention or their motor actions to control technology, as simply as that, right? So I think
Hmm.
about moving my hand, even though it can't move, I can still pick up those signals and use those as an input to allow these devices to be controlled in an intuitive and dexterous way. So that's really that key piece of how do we extract information from the user, or how do we provide a haptic feedback. And then the question is, okay, so we've got this interface that's extracting and providing information from the user, and we've got this physical robot that's interacting with the environment. How do we link those two things together? And that's really that third piece, which is the bio-inspired artificial intelligence, which is really a way that we can communicate between these two systems. And we use neural networks and deep learning and machine learning and all these other different types of buzzwords, if you will, that allow us to interface between these two technologies. And as we're taking information from the human nervous system and converting it into usable information, we're also learning a little bit about how the nervous system operates naturally and how humans motor and tension changes over time and how they learn. And that can actually then influence how we design some of those algorithms in a way that they're more, biologically realistic. And that's where that bio inspired piece comes from.
Awesome. And I love that you talked about intention when referring to BCIs or brain computer interfaces because so often people hear that and get a little spooked. But I think it's an important distinction that it's not just picking up on any random thought. You have to actually have intent behind it. Like you're trying to take an action or have effect in the physical world.
Definitely, yeah, and in my case, I've my lab is focused, predominantly on what we call peripheral neural interfaces.
Mhm.
So we're actually working at the level of the peripheral nervous system, not the central nervous system. So the central nervous system would be like your brain and your spinal cord, and the peripheral nervous system is all the nerves and muscles that kind of come out from that. And what we do is we look at the signals that are at the peripheral level of the peripheral nerves and the muscles there, and we use those. And what's interesting, about the peripheral nervous system is that it's a very deterministic system, which means that when you think about an action, there's all sorts of stuff going on in your brain about like, well, should I do that? Should I not do that? Well, what if I did this instead? And that's all happening in your brain. But by the time you actually go to make a movement, right? If I want to make a movement, that information has already left my brain and is now in my peripheral nerves in a very deterministic way, which means that it's a one-to-one action thing. If I have a signal in my peripheral nerve, it means that I was about to make that action anyway. So by using the peripheral nervous system, it helps a lot for us. One, it gets rid of that kind of that spooky,
Mhm.
reading people's minds or whatever
Right.
that could happen. We're actually not. We're just looking at what their physical intention actually is, right? And in the case of a person who has a spinal cord injury or muscular dystrophy or some sort of, neuromuscular condition that impairs their movement, they're still actually intending to do that motion. It's just that, for example, they've lost a limb and they can't make that motion because the physical hand doesn't exist anymore. So that's another really unique aspect about working at the peripheral nervous system. But I think another cool thing that we do a lot, is that it's actually really complicated to try to understand what a person's brain activity is
Right.
doing. There's like so much more science and engineering that needs to take place before we could do that effectively. And in contrast, the peripheral nervous system is actually very easy to understand. Like, the inputs and outputs are very easy. It's like, imagine trying to open up a computer and figuring out what a computer is doing by, like, taking apart the motherboard, like, that would be really hard to do, but if you just had a keyboard and a mouse, like, you could probably figure out how to work a computer much easier because those are the inputs and output systems, right?
Totally. And then how did your research collaboration with Reality Labs and Meta ultimately come about?
My research had actually been supported in a long time back from, the DARPA agency, so the Defense Advanced Research Projects Agency, had originally funded some of my research. And under that time, I actually worked with Steph, who worked now on. And so we had gotten connected through some of those connections. He had kind of been familiar with some of the work, and I saw a while back that you know, some of this work was coming out from Meta, and we had been similarly developing some of our own internal wrist-worn EMG devices. And so because of some of our connections there, we started talking and brainstorming this idea about, what we could do in terms of, developing the technology further in a more collaborative way. So it was a little bit about, us kind of having similar shared interests and similar expertise, and then identifying areas where we could, strategically support some of the work that Meta's doing, while also advancing some really unique scientific questions that help the field more broadly. And so one of the key pieces we're going to be working on, which we're really excited about, is trying to see how accessible EMG at the wrist, particularly using the meta neural band, and how well that could work with different users, that have different neuromuscular conditions. So, a person who gets a metaneural band, if they have a spinal cord injury or ALS or
Mhm.
muscular dystrophy, does that technology still work for them? Some of the challenges you might face is that every person is a little bit different. And when you are looking at their nerves and their muscle signals, that could change if they have some sort of different type of condition that affects their nerves and their muscle behavior naturally. So what we wanted to look at is, how does that performance impact individuals, that just try to put this device on right out of the box, that would still work for them. And if not, are there ways we can inform the design now, early on in the process, to make sure that it works for everyone, right? what's really key for us is to be able to um, work directly with the users who have various different types of neuromuscular conditions and co-design with them the technology so that it works closely with what they want to do and also works with the broader infrastructure and support that's been developed here.
Awesome. And have you had a chance to get hands-on, for lack of a better term, with the metaneural band or not yet?
Yes, I've used it myself, and it's very impressive. I've worked in this field for quite a long time, so I've been developing, algorithms that understand motor intention from EMG signals, both at the forearm and at the wrist, even using implanted devices in individuals with, chronic, impairments and things like that.
Mhm.
So I've been working in this area for a while now, and it's extremely impressive to see what has been created through Reality Labs. The technology is very robust. I mean, it's a commercial product, and it feels like a commercial product. Whereas I'm used to working in the
Right.
research realm, and there's knobs. You're always tinkering and trying to get it to work just right. But it's really impressive to see that you can put this thing on with zero level of training or interfacing, and it just works. And it works not only like well, but it works better than almost anything ever I've used it before in this field. There's so much potential with it. That's why we're really excited about this partnership. Is that I can just imagine now that we have a really robust way of taking a person's intention of their movement and turning it into a digital signal through a robust and a low cost device like the metaneural band. I mean, this opens up so many different research avenues and ways we can explore that as an accessibility tool, as a broader human computer interaction tool, and more as like a health and fitness and wearable technology. So I think it's really beginning to unlock a whole new realm of capabilities and exploration and research. And so these types of partnerships are awesome because they allow us to leverage such a strong, well-designed, engineered product in a very robust way, and then explore all sorts of new use cases that can make the technology more accessible, more usable, and ultimately improve quality of life for a greater number of people.
Absolutely. And you've mentioned accessibility and accessible design, which they say accessible design is good design. It's smart design. Which is part of why EMG as a consumer technology is so exciting. We've been talking about EMG for a while on the blog, but for those who aren't familiar, can you give us sort of the elevator pitch for surface electromyography? How would you explain that to a friend or a family member?
Yeah, so when we think about moving our hands, right,
Hmm.
this information starts in our brain as an electrical signal. It then travels from our brain down our, spinal cord and then to our nerves. And those nerves then send those electrical signals as these digital pulses down to our muscles,
Uh-huh.
where when it hits our muscle, it actually causes another electrical signal from the surface or from the muscle itself, which then propagates through space and time across the surface of the skin and creates a small little electrical field that you can record, on the surface of someone's, forearm or on their wrist, right?
Hmm.
And so when we think about moving our hand, that information, when we're actually moving our hand, there's small electrical signals all across our surface of our skin that is actually happening as we're doing different things. So what EMG does is it basically listens to those small signals all across the surface of the skin. It amplifies them, and then it uses artificial intelligence to take those signals and translate them into what the hand was actually doing. And so the way that this system is built is you basically take an individual and have them do a variety of different hand movements, or in the case of the metaneural band, you have large numbers of users demonstrate to a computer algorithm how these signals correlate from the wrist to the actual intended motion of a person's hand. And you build up an AI model that can then map those things in real time so that the next time a person puts on a band and it starts seeing these electrical signals, there's already kind of a mapping, if you will, or a lookup table that can kind of go back and find, what those motions actually correspond to. Things like clicks, swipes can all be interpreted relatively easy from these electrical signals now that we have this database of what they look like across a variety of different individuals. And so what's really cool about that is that it allows us to use basically simple gestures from our hands using a smartwatch essentially that can or a wristband, right, that allows a person to interface with technology and kind of convert their physical actions into digital command. And because it's been built off this database, right? It's been built off a database of individuals. The question is, how diverse are those individuals?
Mhm.
Are those users representative of every possible person? And is that technology truly accessible? And so some of the questions we want to look at is like, well, does this work for individuals who have, for example, muscular dystrophy?
Mhm.
Or, for example, a person who maybe lost a limb? Do their muscles behave in a different way that don't quite fit the standard box, if you will, for them to be able to use this technology right out of the box? And so part of it is allowing individuals to customize the approach so
Mhm.
that then it can, work specifically for them. And the other part of it is, working with them to identify, what types of things make sense. It might make sense for us to do, swipes and clicks, but like, what if you've never had a hand before in your life?
Mhm.
Like you were born without a limb, then, that process of figuring out swipes and click might not make it much sense to a person who's been paralyzed or lost a limb. And so allowing them to kind of have their own say in how these things are designed can ultimately create a technology that's more inclusive and more accessible to a variety of different individuals. And on the other side, it actually makes this technology even more impactful. And from a commercial and commercialization standpoint, it allows a much larger user base, which then overall, definitely helps bring the technology into a larger market and can also then allow, more input, more diverse users, which can then continue to grow the accessibility of the technology.
If I'm remembering correctly, you've aligned on smart home controls as sort of the primary focus for the study. I'm just curious how you sort of narrowed in on that particular area to look at.
Yeah, so for this initial collaboration, we're actually looking at kind of three different things. The first is we're looking at, just out of the box, how does this technology work for an individual with different neuromuscular conditions? And then can those things be tweaked and co designed with those users to create a more accessible and more effective interface? That's kind of the first thing we're looking at. And that'll mostly be done on a computer, working with kind of some existing kind of tasks that you might do on a computer interface. The
Mhm.
second key part of this project is to take those commands that we're getting from the metaneural band from individuals with different neuromuscular conditions and testing them in a way that we could use this as an assistive technology. So right now, the meta band can be used to control, AR glasses. It can also potentially be used to control computers and other things like that. But a question is like, how does that necessarily help a person who has some sort of physical disability that does not allow them to like, move around and get up and down and do all these other sorts of activities? So one of the things we want to do as an initial proof of concept is if we could have individuals use the metaneural band to control smart home devices, right? Right now, smart home devices, like most AR glasses, are controlled using voice command. There's a lot of limitations there, in allowing you to be able to do over or versus subtle types of movement. So what we're really interested in doing is can we use the metaneural band to make gestures to control different types of things? You can imagine swiping left, right, up, down to go through, your Netflix style menu on your smart TV. You could also imagine, gesturing up and down or different types of motions to allow you to turn the lights on and off. And the reason we're really interested in exploring this as well is because we've seen firsthand the power of smart home technology as an extension of a person's care team. Because in the hospital that I work in, which is the Craig H. Nielsen Rehabilitation Hospital, we actually had every patient room fit with a variety of different smart home devices. So the patients can actually control the lights, the TVs, the blinds,
Mhm.
the bulbs. They can call for a nurse. They can open the door. They can do all sorts of different types of things like that, all just based off of their, uh, voice commands or by touching a tablet. So right now, patients in this hospital can use their voice commands or use a tablet to basically interact with all these different types of technology around them. And it has a tremendous impact on their independence, their quality of life, and the care that they receive because they can get, the people to help them with the different types of things they need in a much easier and more efficient way. Um, so the idea is like, well, rather than them having to use voice commands or touch a physical tablet, which many of them can't because they can't physically move, what if we could use their intention, their motor intention from the metaneural band to control these types of technologies? So That's the first one is really this idea of controlling the computer. Second one is controlling the smart devices. And then our third major part of this project is to allow people to control a physical device that they can interact with to get back into doing like real world tasks, like things that they love. And Utah is a really unique place because we've got beautiful mountains surrounding us. We've got the 2034 Winter Olympics coming back to Salt Lake City. And we have a lot of people in this area that love to participate in outdoor recreation, like skiing. And so, what we're really interested in doing is using the metaneural band to allow people to control a ski, a physical ski, to go down the mountain. So, at the University of Utah, we developed a device called the Tetra ski. And this is a physical ski that actually can actuate and move that light left and right and can change the wedge angle of the skis. Right now, that device is used by individuals with muscular dystrophy and spinal cord injury and other complex things like quadruple amputation. And the way that people control this is they actually use sips and puffs of air. You actually would breathe in or breathe out to control the skis to go left versus right. And as you can imagine, that's not a very intuitive way to control technology. What we're trying to do is to see if we can use the metaneural band to allow people to control the ski with greater efficiency and with less cognitive demand. So they don't have to think as much about sips and puffs and they can just get back to doing what they love to do, which is ski on a mountain.
Mm-hmm. That's really exciting. And I'm curious, what kind of motivated your decision to get into the accessibility space, both as a researcher and also from a design perspective, from a patient care perspective? Just would love to hear a little bit more about that.
Yeah. So I think many people get into this space originally because of things like science fiction, right? Where it's like there's these really cool ideas about, how can we control technology with our thoughts, right? Like, can we just think about moving these things and make it happen? Can we interact with, holograms and feel things and, have this kind of telepresence or telepathy type way of interacting with technologies? So I think at an early age, those types of things really got me interested in this field of neurotechnology, right? And then I actually ended up while I was a student and doing my undergraduate in biomedical engineering,
Uh-huh.
I got an opportunity to do a summer research program at the University of Utah, where I actually got to work with a variety of different individuals who had some implanted devices
Hmm.
who were actually using this. And this was an individual who had lost their hand, who had a neural interface that allowed them to ultimately control a prosthetic hand, and allow them to have this kind of interactive, Luke Skywalker arm that allowed them to get back into doing real world tasks. And when I was working with an individual who had an amputation, they specifically said that, losing a limb was like losing a family member, except they were reminded of it every single day. And that quote really stuck with me, and it really inspired me to think about, how impactful this type of technology really can be. Having lost multiple family members myself, I know that kind of the trauma that goes with, loss, but I can only imagine having that amplified every single day with, lack of autonomy, lack of accessibility, chronic pain and all these other challenges. That So I think that was kind of a really inspiring moment for me that kind of solidified my interest in this technology, not only as a cool science fiction realm, but a really cool way that we can deliver, um, you know, technologies to individuals that truly make a difference in their quality of life.
So I know that it's pretty early days, but looking at the sort of broader research agenda that you have, the hypotheses and questions that you're looking to investigate, what has you most excited? What are you kind of most curious about? What do you think might be the most surprising thing to come out of this? Or is it really too early to say?
I think one of the things we'd love to be able to say from this study is that the metaneural band can be used for a variety of different individuals with neuromuscular differences, right?
Hmm.
And I think one of the things we really want to be able to say is that not only can it work, but that we've worked with those individuals to actually develop a technology that specifically works for their needs and built around, their interest and their goals.
Hmm.
And we have some initial ideas of how this technology could be used in an assistive way, like to control smart devices or to allow people to control adaptive recreation equipment. But ultimately, I think what's really going to be a key outcome of this is just learning and working and co-designing with these different individuals to create a technology that really does, things that we can only begin to imagine, right? But I mean, everyone's going to have their own interests and their own story. And by allowing people the ability to use this technology to support themselves and their own independence and their own independent goals, it really will kind of open a variety of different ways. And so as a scientist, this is something that, is really exciting because it's a platform technology, right?
Hmm.
And you can use this technology to empower others, right? And if we can provide a really robust way for individuals to interface with technology. I mean, like technology is only growing and growing, and there's more and more different types of assistive things out there. But imagine being able to control a wheelchair, control a ski, control a sailboat, control a smart home system, control a car, right? Even all these different types of things could be done. And for individuals who have traditionally been left out of society and haven't had the opportunity to participate in a lot of these things because of some sort of unfortunate neuromuscular condition or injury, you know, this is an opportunity to level the playing field. And it's an opportunity for individuals to be able to get back into, greater participation in society and with all the positive things that can come from that, whether it's quality of life or greater economic and growth and all sorts of different types of things. So I think, across the full spectrum, I think this is just a really exciting opportunity to see the many different directions that individuals will want to use this technology to improve their quality of life.
I love that. And I think that's one of the things that's so just fascinating about EMG, surface EMG, and also the intersection with AI is that as you said, the importance of this technology working right out of the box is so key. But at the same time, there's the potential for the technology to sort of co-adapt with the user over time as it gets to know your own personal kind of idiosyncrasies and movement patterns. So it'll be really interesting to see how things evolve from here.
Yeah, and I think, another key piece of that is that, you know, people's neuromuscular capabilities change over
Mhm.
time, right? I mean, even just, the everyday person, as you get older, your muscles change, right? Your strength changes, but imagine someone with, for example, ALS, right?
Mhm.
Their capability changes at a much faster rate and in a
Right.
much different way than someone else. And so, this type of technology has the capacity to potentially evolve with a person on that level as well,
Mhm.
right? And so these are some really interesting questions that could come too, which is like, how do these algorithms adapt over time and maintain robustness and maybe do it without even anyone having to ask it, right?
Mhm.
Like, what if it could just do that behind the scenes and you wouldn't know? And if it's already adapting in real time, then eventually it knows something about the user state to adapt to it. And if it knows something about the user state, maybe that could also inform diagnostics, right? And maybe it could help a person who has ALS, know about their progression and where they're going. So I really do think there's so much potential about this type of technology to not only be a user interface, but to also potentially be a diagnostic. And if it's a diagnostic, it could be used as a rehabilitative tool. And so it could really fundamentally change a lot of different opportunities for us to, support individuals with neuromuscular conditions.
Awesome. Well, we've covered a ton of ground. This has been really, really fascinating. Is there anything that we didn't touch on or talk about that you wanted to add?
Yeah, I think I'll do my standard.
Mhm.
I think all of this work is a very large interdisciplinary project that involves quite a few different individuals. And so, I'm grateful to be working closely with, industry partner, Meta in this case, but also, the University of Utah has quite a large number of people who are involved in this project as well. So my colleagues in the College of Engineering, as well as in the School of Medicine. This includes, occupational therapists who are going to be working directly with patients, but it also includes engineers and PhD students and scientists. And there's quite a large number of teams that will help make this type of technology possible. And it also is built around, foundational work at Meta, as well as foundational work that's been supported by Meta and other, government institutions like the National Institutes of Health. We talked about some previous work that would come out of a lot of this work from the DARPA or the Defense Advanced Projects Agency, as well as the National Science Foundation. So I think there's been quite a large number of people who have helped support and get this technology to a point where it's at now. And, so I'm really grateful to all the people who have played a part of this. both at Meta and at the university and in the US and the scientific community in general. And I'm also really excited to be collaborating and working with a variety of other individuals in this space going forward. And so I guess that would also lead to one other point, which is
Mhm.
that, I really do think that this is a very emerging field. There's a lot of potential here. And I think this is an opportunity for others who have not particularly been involved with EMG to get involved because this type of technology in the metaneural band is, arguably going to be, the next best, or the next really, intuitive way that we interface with technology. And now is the opportunity to kind of start exploring a lot of these questions. And I think it's really great that, we have opportunities to work closely with groups like Meta who are pioneering this technology to make sure that we're doing it right from the ground up, right? And really making sure this technology is accessible and learning about all the different possible ways it can be used and building the technology towards the future that we see, right? The positive future that we want to have happen.
Yeah, very well said. Well, thank you, Jake. This has been amazing. I really appreciate you taking the time to sit down and chat with us and can't wait to see how the research pans out.
Thanks so much. Yeah, it's been a pleasure talking with you as well. And yeah, we're looking forward to all the positive things that'll come from this.